Hello and welcome to Liqid's webinar on Composable Supercomputing for HPC Workloads. Without further ado, let's begin our webinar hosted by George Wagner, Director of Product Marketing, and Aaron Moline, Senior Director of Engineering for Liqid.
First, we're going to talk a little bit about supercomputing itself. It's been around for a while, and we've had tons of technical advances through this, right? It's changed the shape of the world. We've cured diseases. We've understand the universe better because of it. And I think we all understand that it's a really valuable resource for us. But with it comes a few challenges, right? We need to build these supercomputers in these HPC environments with 3 to 5 year lifespans where we don't know the workloads, and the workloads are getting increasingly more complex, needing more resources. We need to plan for those in the buying cycle, which is today for 3 years from now. We also have problems with things like efficiency. You have a large number of resources in this, in your HPC clusters. They're not all being utilized at the same time. You have captive resources in machines that aren't necessarily being utilized to their maximum efficiency. And we also have problems, the age-old problems with just regular data centers of power and cooling and how to spread those loads out and cool and power more efficiently. So one of the big things that we want to look at is this right here is a chart of GPU adoption over the course of the last few years and looking out forward. GPUs are becoming more prevalent, and we are utilizing the parallel capacity of GPUs more and more and more. As applications are starting to catch up and be rewritten to take advantage of GPUs, we're seeing the need for more and more GPUs in HPC environments. Right now, they are very CPU core centric because that's where a lot of the applications are doing their processing. But we're starting to see a lot more of these applications being rewritten to take advantage of accelerators, GPUs, FPGAs. And that is really where the trend is going. These are expensive resources, and we want to be able to utilize them in the most efficient way possible. And that's where we can have some benefits of a composable infrastructure. And to kind of explain composable infrastructure, I'm going to hand it over to George here for that.
Fantastic. So my name is George Wagner. As Melissa said, I run product marketing here and technical marketing here at Liqid, and I'm really excited to go through and give you an overview of our composable disaggregated infrastructure. But I think it's important beforehand that we kind of set the stage, right? Understand the challenges that you're running into from an HPC standpoint, infrastructure-wise. So let's go ahead and take a look at how we arrived at this moment in time. So really, for the last 30 years, whether it's HPC, virtualization, or just standard computers, if you go under the software, if you look underneath the software, it all looks the same. Essentially, it's x86 hardware, right? x86 servers tightly coupled in a box. And really, what's the issue with that? There's not an issue from a usability standpoint, but when it comes to using it at the scale that you all are using it at, this definitely presents some challenges, right? This is a static infrastructure. And when I mean static, right, you are confined by not only the box itself, but also the number of PCIe slots that exist in a server. So you need to make some hard decisions, right? Is this an IO-intensive workload I'm going to be working on, or is this data-intensive? Am I going to be using GPU or more NVMe flash? Those are decisions you have to make, and you're probably not going to be able to put everything you want into a single box, right? Because of that confinement. When it comes to scaling, it can be painful. Let's say that you do have PCIe slots available to add additional resources. That's going to require you to schedule downtime to go in with a screwdriver, crack open that system and add additional resources. Or let's say you do have a server that today has support for 2 GPU. Those GPU are in the box, but you need a third. What's the answer? The answer is probably going to be buy a new server, right? Or go and scavenge and create a new one. That's just the way it is. And if you have to go out and buy a new server, guess what? You'd be talking 6 weeks to 6 months of time waiting for that to be ordered, shipped, and stood back up in your data center. So scaling can definitely be a pain. And then from a utilization standpoint, those resources in the box, they're trapped in the box, right? They're stranded in the box. And when we're talking about accelerators, GPU in particular, that's a very expensive and very valuable resource to have stranded in a box. They also force you to make undesirable decisions. So let's say that I have the need for a server with one GPU, yet I only have a box with 8 GPU available to me. What am I going to do? Well, if that job needs to start now, you're going to spin up that 8 GPU box, right? And you're going to have a ton of waste. So, x86 is not going away. It's been around since I've been around, and when I was in IT years ago. But as far as the way that it's configured, the way that it's composed, that can definitely change, and that's what we're doing here at Liqid. So what we're doing is we're enabling our customers to go in, especially our HPC customers, to go in and dynamically compose those disparate resources that they have in their data center to create bare metal servers in really any configuration. And the benefits we provide across HPC are really accelerated time to value. So for example, waiting 3 weeks when you're trying to work on a cure for a disease is too long. So being able to spin up, in the case of Liqid, we can spin up a bare metal server in any configuration in just a matter of seconds. And when I say any configuration, I'm not kidding. I mean, really kind of sky's the limit. And we'll talk about that in just a moment. But we can meet any workload requirement. From a scalability standpoint, you're no longer breaking out screwdrivers and having to pause workloads to do upgrades, right? All that can be done online. And then from an efficiency standpoint, as Aaron mentioned, we looked at the growth of GPU over the past several years and into 2025. Right, that's not slowing down. And if you're not utilizing utilizing those resources, putting maximum effort behind that, you're really wasting time and money. So increasing efficiency from that standpoint is something that we do an excellent job on. And because we have a cloud-like way of composing, it eliminates the amount of time that you're spent racking and stacking servers and all that, unless you be more strategic to the business. So what is composable infrastructure, right? So instead of using rigid methods to create HPC systems like x86 servers all on their own, what we do is we enable our customers to disaggregate and pool all their critical resources together, right? And by critical resources, I'm talking about your GPU, right, for the data-intensive workloads. Talking about NVMe for the IO-intensive workloads, NVMe storage, NICs, FPGA, etc. All of those, pull those together and put these resources in enclosures or trays, if you will, in the data center. Right, so they're completely separate from the compute resources themselves. Right, and then the compute resources can be something as small as a server with CPU and memory. Right, and we take that and we plug those enclosures into high-speed fabrics, PCIe, for example, in this case, and in many cases just due to the low latency. Right, we're talking about 150 nanoseconds latency in Gen 4 PCIe. And then from there we use our software, right? At the center of any composable infrastructure is the software. That's where the magic happens, right? And we can compose servers in any configuration in seconds. And you don't have to go out and like I mentioned a few minutes ago, when you have the need for one GPU, spin up or plug in an 8 GPU server, we can create exactly what you need in seconds. I should say you can create exactly what you need in seconds. And it can meet any workload requirement. I kid you not. I mean, it could be something as absurd as a one-use server with 20 GPU. Right? All you need is imagination and resources. Right? But if you think about what we're doing here from an infrastructure standpoint, below the software, we're essentially extending the PCIe bus outside of the server, right? So kind of putting your head around how it works. That's effectively what we're doing. But the real benefit, the real value of Liqid is what we do at the software layer, right? This is very unique. I used to be an IT guy myself, and so I'm definitely a big fan of what's happening in transformative technologies like we're doing here in Liqid, and I believe it's definitely making a difference. From a management standpoint, we're using we have CLIs, right? We have a web GUI, and we also have APIs, so you can to connect and work with northbound applications like Slurm, which Aaron will get into here in just a little bit. But bottom line is we can do things much faster and give you much more of agility than you've ever experienced in your environments. Let's say that I have a server. Things are always changing, right? The truth is, as my old science teacher told me, the truth is always changing. That happens in IT as well. In HPC, you think in terms of jobs, right? And jobs start, jobs stop. When a job stops and you still have resources in a server and those resources need to go elsewhere, with Liqid, it's as simple as moving those resources back into your pool. Simple as that, right? So it allows you to be more agile and add those resources where they're needed as you're spinning up new jobs. What about scaling? Well, instead of scaling by having to crack open the server and look at the limited amount of slots you have and make those tough decisions, with Liqid, it's all done via software, right? Add what you need when you need it. Never have to touch a screwdriver ever, which is fantastic. And beyond that, let's say a newfangled technology comes out. Let's say there's new breakthroughs happening in FPGA. Well, rather than having to buy a bunch of FPGA cards and jam them into your server nodes, you can simply add an extra enclosure, an additional enclosure of FPGA, and begin composing those into existing servers immediately. Oh, and by the way, is this something that has to be done with brand new servers? Absolutely not. You have existing servers in your environments today. I'll show you how this system is built momentarily, but the answer is absolutely you can use this with your existing servers today and the new servers as you continue to acquire them for your projects. From an efficiency standpoint, right, it's all about maximizing those usage, right? So if we're talking about GPU, if we look at normal utilization for a daytime workload or even a 24-hour workload, we're thinking about doing, you're hoping to get maybe 50% utilization. With composable infrastructure, especially Liquids, we want to nail that down to about 100%. I mean, if we can get 100% utilization out of all of our GPU, we're doing something good. And you all are judged on how fast you can get results, right? Get those jobs done, the jobs finished, the jobs completed. Well, if we're able to compose the systems we need, we can get faster systems, right? We can get more horsepower into systems, which enables better parallelism, which ensures that we get jobs completed faster. And finally, reducing data center costs, absolutely. You're spending less time, as I mentioned a few minutes ago, cracking open and upgrading servers and moving and shifting and lifting within the data center. You're being more strategic to your organization, whether that's university, whether that's a business, science, etc. So that's definitely huge. And because we're dealing in this is more like cloud on-prem. It's something you're probably all familiar with from automating these types of processes. In the cloud, just automate them on-prem. So what does this look like? Well, it's simple. Actually, you know what? Before I go any further, let's stop and ask if there are any questions out there.
Hi guys, there are a couple questions.
Okay.
I'll read them both. The first one is, you're discussing PCIe and Ethernet fabrics. For HPC environments, we need InfiniBand. Is this supported also by Liqid Orchestration?
Yes, this is Aaron. I'll jump in here and answer that one. Yes, the answer to that question is yes. We can compose over both basically PCIe Gen 3 and Gen 4 today, as well as InfiniBand and Rocky. So Rocky over Ethernet. So we can compose essentially. Now there are some limitations on the Ethernet front. We can compose NVMe and even GPUs over Ethernet and InfiniBand. Things like NICs and FPGAs are not supported over Ethernet today. All right. You sort of answered the second question in that first question, but there's a third question. After reviewing your site, I understand you have Optane solutions that show to be faster than native Intel Optane. Could we deploy these in composable disaggregated racks? Can they also be used as extension to DRAM memory? So the answer to that, to both those questions, is yes. So we can have a further discussion on our storage products, but yes, our Optane is roughly about 3 times faster than Intel's Optane. We are leveraging Intel's Optane to do that, but due to our unique architecture on our storage products, we're able to get about 3 times more performance. Those are available to be composed in disaggregated, and you can either use those as just really fast block storage, or you can use them in conjunction with Intel's IMDT drivers to do memory augmentation. Okay, just one more and then we can keep moving forward. Okay, perfect. It says, can I share a PCIe device between 2 clients, like a storage adapter? So the answer to that is both yes and no. So I'll explain a little bit. We can share devices between compute nodes. When it is assigned to a compute node, that compute node has basically unfettered access to that. We can't simultaneously mount a device to 2 separate servers. We are in development on ways to enable that, but today we do not do that. But you can share devices between servers based on their needs, right? So if a server needs a GPU for a certain job, and that job finishes, then we can take that GPU and move it to another server, and so it's more of a time-based sharing versus a multiple access sharing. All right, and I will kick it back over to George, and he can continue with kind of the what this looks like conversation.
Right. Yep. Thanks, Aaron and Malaysia. Yeah. So this is just an example of kind of what physically a deployment would look like, really simply, right? So we're talking about a compute node. In this example, we're showing a Liqid server, Liqid branded server. But as I mentioned, we are agnostic. We don't have affinity for any server type. You decide what you want, what works best for you. You take and plug an adapter card into that server, essentially an HBA, depending on if you're using PCIe or Ethernet, and then from there plug it into a fabric switch. The switch you're looking at there on the screen is our Gen 3 PCIe fabric switch. We also have a Gen 4 coming down the pipe. Lower latency, obviously, and then you have the kind of downstream devices, if you will. So flash, networking, GPU, those J boxes that plug into that fabric, and that's essentially what that's physically what enables it, and then of course the software layer on top is what actually enables it. But as I mentioned, we are vendor neutral. You can select whatever devices you want and put them into the enclosures. As the question came up about Optane, we do have the fastest NVMe add-in cards in the world. So if you are looking to add extremely fast, low latency cards into your environment, in your composable environment, definitely we can have a conversation around that. And then from an offering perspective, looking more at the right side of the screen, these are the enclosures, Liqid enclosures, so for networking, right? So you can compose networking, storage, that big box there in 3/4 of the way down is the Sumo. It actually holds graphics cards, so up to 20 GPU or 20 adding cards. And so that's definitely an option. And then below those are also compute nodes down at the bottom. But that's just kind of an example layout if you had like the full-blown solution. And of course, you can add as many more devices as you need to, enclosures, etc. But that kind of gives you a flavor for kind of what we're doing from a product standpoint. And so what I want to do now is pass it back over to Aaron. Aaron's going to go through some use cases and give you an idea kind of how it works in your environment.
Perfect. Thanks, George. So now that we have an overview, let's kind of switch back to kind of the more HPC-centric view of this. One thing that we came to realize early on in our adventures into HPC is really in order to make this all work, we need to integrate with basically the tools that many of the HPC people are using today. So we've developed a Slurm plugin, and we can go deeper into that. It's probably a whole separate discussion. But essentially, the takeaway from this is we enable Slurm to understand the dynamic nature of our fabric underneath. So when Slurm gets a job that needs 10 GPUs, we will go create those servers and provide him a server with 10 GPUs. If he needs NVMe storage, if he needs any resources, we're essentially building those servers up and presenting them to Slurm. And then Slurm essentially just does its job as it normally does it. It has a node that meets the criteria and launches the job. So our solution fits essentially seamlessly as far as the user is concerned into existing HPC environments. The individual researchers or people submitting jobs to these machines don't have to do anything different. They just need to specify the resources and the types of machines that they're looking for, and as they already do today. And then let's look at this a little bit more. We looked at some simple examples. This is a little bit more at scale, right? And this is more of a traditional type of HPC environment. So this is our reference architecture for what we're showing you here is 3 racks. This can be extended out to essentially as many racks as you need. So in this reference design, we've got 96 nodes. So these are 2U 4-node servers because again, now we can go super dense. We can go to half-U servers because all we need in those servers are CPUs and DRAM. Everything else can be moved out of that server and made composable. So we can pack a ton of density into into the server platform. We also have 48 terabytes of, again, we had that Optane question. We have 48 terabytes of NVMe or of Optane that can either be used as super low latency block storage or can be used as memory augmentation. We have, a petabyte, roughly, of NVMe for scratch space. So if we need any local storage to complete our jobs, we can just pull up the storage that we need. And in this design, we have 144 accelerators. So these could be GPUs, these could be FPGAs. We're having conversations around things like TPUs, other things that can accelerate our performance. And those are all native in here, and we can do any-to-any composability. So I can have one of these servers have 20 GPUs. I can have one of these servers have 100 NVMe drives. I can build whatever server out of this that I can imagine. The other interesting thing here is it kind of breaks some of what we do in HPC today is, and we've actually had a lot of customers that really liked this design for a couple of reasons that really have not a lot to do with composability. We're providing standard racks. All of these racks have the same power requirements, have the same cooling requirements. We no longer have the corner of the data center that has all my GPU servers that are essentially a heat island in my data center. I'm spreading that out. I can cool that more efficiently. I can power that more efficiently. And even things that we don't often think about is now I have one standard node. I don't have to carry spare parts for all different types of nodes, a 4U server, a 6U server, a 1U server. I have a standard node. I can make it whatever I want. I can make it a GPU node. I can make it a high memory node. I can make it a login node. I can make it whatever I want when I need it. And my maintenance, my spares, all of that stuff becomes simpler. So I get this question often, especially talking to some HPC customers, is, okay, this is really cool. This is some really cool technology. What does it mean for me, right? I'm being judged on my supercomputer in my HPC environment is being judged on how much work it can do. What does this do for me? So there's actually a pretty simple example and one that one that actually came from a customer conversation. So in this simple example, say that I have 4 researchers, right? They're all submitting jobs. They're all submitting, let's say they're doing training, right? And they want, high GPU counts. My environment only has 2 servers that have 8 GPUs in them. Well, now they're kind of competing for those resources, right? They all submit their jobs at the same time. The first 2 people that get it in the queue first, they start running their jobs immediately. Then the next 2, now they're sitting in the queue. They're waiting for those 8 GPU machines to become available. So in this case, in order to get all of these jobs done, it will take me essentially 2 days to get all of these jobs done. We fast forward here and look at a more composable solution here. It's those same 4 researchers. It's that same job. They know it's going to take them 24 hours with an 8 GPU server. They submit those jobs to Slurm. We can actually build different machines in Slurm. So now all of a sudden we say, hey, they can now request up to 20 GPUs per server. And we can go build those, and we can go build 4 of them. Now all of their jobs can run not only faster because they have 20 GPUs, now they can run all in parallel. So now we've taken what was 2 days to get those 4 jobs done. We've now reduced to 10 hours. So that's almost a 5x improvement in completion times for these 4 jobs. So that's the takeaway message, right? Is essentially the composable solution underneath your HPC environments enables you to run more jobs faster. And that's the key value here to get from this. And I'll pass it back to George to sum things up.
Yeah, thanks, Aaron. So yeah, I mean, basically, this is a lot to take in. We have 30 minutes to go through a new technology, exciting technology that we believe can make a difference in your environments. I mean, I hope you felt the same. The bottom line is it gives you a lot more, it gives you more flexibility, it allows you to spin your systems up much faster, and increases your utilization, ultimately allowing you to finish your jobs much faster than you've ever been able to before. We'd like to go to the next step and have a deeper conversation with you, potentially giving you a demonstration of the software as well. If you'd like to do that, please reach out. You can go to our website there at the bottom of the page, liqid.com. You can follow us on Twitter, but most importantly, give us a call. Right? There's a phone number at the bottom of the screen. Give us a call and set up some time with us, and we'd love to go through a little deeper and actually answer specific questions that are important to you and your environment.